So in the previous session, I briefed you a little bit about rational numbers, and unequivocally I mentioned that a rational number is one that could eventually be expressed as the ratio of two integers, the denominator not being 0. And in the lowest form, it could be expressed as the ratio of two integers that have no factor other than 1 in common. That means in the form p by q, where p and q are not just integers, but have no factor in common other than 1 and are referred to as co-prime or relatively prime. Now, it's easy to check if it's a number is rational. It's easy to check. But if a number is not rational, then the check is not that easy. To check for rationality of a number, if indeed it is rational, is not a tall order. Be it in its decimal representation or be it in exactly the form desired, which is the ratio of two integers, it's not difficult to check. It requires no special effort, no special care. But to check if a number is not rational requires special care, special techniques, and direct methods are not deployed to check irrationality of numbers. Numbers that are not rational are irrational numbers. Numbers that are not rational are irrational numbers. So, essentially, if we can't express as ratio of two integers, an irrational number cannot be expressed as ratio of two integers. That means it can't be expressed as p by q, where p and q are integers, right? And q is not 0. And therefore, an irrational number can't be expressed in the form p by q, where p and q are integers. I is the set of integers where p and q are integers, and p and q have no factor other than 1 in common. That means if you want to express an irrational number in the form p by q, where p and q are integers and have no factor other than 1 in common, then you will fail to do so. And therefore, if you cannot express a number in the form p by q, ratio of two integers, and especially as ratio of two integers that have no factor other than 1 in common, that means as ratio of two co-prime integers, then the number would be referred to as an irrational number. Now, being able to express a number in the form p by q is an easy check. But not being able to express a number in the form p by q is not that easy a check. Now, in the decimal form, see, this is as far as the ratio of two integer aspect of an irrational number is concerned. However, in the decimal form, let me tell you what it means by an irrational number. What it means by an irrational number in the decimal form. That has to be understood and taken notice of. In the decimal form, number 1, it's going to be a non-terminating decimal. However, if the decimal portion of a number is non-terminating but repeating, like I said, 5.33, etc., or 5.62, it's not terminating anywhere, but it's repeating. You see, 62, or 3333 is appearing forever. It's repeating. Non-terminating, but repeating. If that happens, then you end up getting what's called a rational number. But if the decimal portion is not just non-terminating, but is also non-repeating, not just non-terminating but non-repeating. For example, if I had 5.316432159, etc. This goes on forever. This chain doesn't end. And there is no repetition. Do you see that there is no repetition here? No repetition occurs. Non-terminating, non-repeating or non-recurring. Non-terminating, it's not terminating anywhere. And it's also not repeating or recurring. The portion after the decimal is not repeating in any form. And therefore, that means, you can't find a chain after the decimal that repeats. In the earlier case, 5.626262, the chain that was repeating was 62. 62, 62, 62, that was repeating. In this case, nothing is repeating. You can't locate a chain or a string which is completely replicating itself. Therefore, numbers of this form are not rational numbers. These numbers are irrational numbers and they cannot be expressed in the form P by Q, where P and Q are integers, and therefore they also cannot be expressed in the form P by Q, where P and Q are not just integers but also have no factor other than 1 in common. That means they are co-prime numbers. Now, it then becomes important for us to see and examine how we could figure out whether a number is irrational or not. If a number given is rational, then the check is very easy, I told you. But if a number is not rational, that means if a number is irrational, then to be able to very conclusively evaluate its irrationality is a little bit of a different technique with which you would become familiar from now on. It's not difficult, but it's different for sure. It's not the regular technique. For example, if I have a number like root 2, if there is a number like square root of 2 and I want to see if it's rational or not, I want to see if it's rational or irrational. Well, when you do not know whether a number is rational or irrational, then what you do is you assume that it's rational. When you cannot readily see whether the number is rational or irrational, then you assume that it's rational. That's the rule of the game. I repeat, whenever, as and when you find numbers about which you are not very sure, you cannot readily conclude their rationality or irrationality, then you assume that those numbers are rational. So root 2 is something that I cannot readily conceive whether it can be expressed in the form P by Q where P and Q are integers, or it cannot be expressed in the form P by Q where P and Q are integers. I assume for such numbers that they are rational. Let's assume that root 2 is rational. It's only an assumption. Now, the moment I assume something, and based on that assumption, I carry out a set of things. And if it eventually leads to a result which is good and looks fair, then I can assume that my assumption has been correct. But if the assumption is wrong, then down the line, that assumption will show off. It will produce something which is bizarre, which is incorrect. If the assumption is wrong, sooner or later, it will show up. There would be something that would come up that would be glaring and that would very conclusively force you to believe that your assumption has been incorrect. Right? So in this case, let's assume that root 2 is rational. Now if root 2 is rational, then root 2 could be expressed. If this is the assumption, and if it is true, then I can always express root 2 in the form P by Q. I can always express root 2 in the form P by Q. It's expressible eventually in its lowest form. In its lowest form, the lowest form of root 2 then would be let's say some P by Q, where P and Q are integers. Q cannot be 0 because division by 0 is terribly illegal. And P and Q have 1 as the only common factor. Only common factor. Right? Eventually, I'm saying root 2 is rational, and therefore is expressible in its lowest form. In its lowest form, I say it's p by q, where p and q are integers, q is not 0, and the only factor common between p and q is 1. Right? Let's assume this is true. Let's assume this is true. Now, based on this assumption, let's carry out some more manipulations. Now, if I square, I get p squared is 2q squared. Yes or no? Square, this becomes 2, this becomes p square by q square. So p square by q square is 2. P square then becomes 2q square. Now, what does that mean? P is an integer, so p squared would be an integer. Q is an integer, so q squared is going to be an integer. 2 times an integer is going to be what? An even integer. 2 times q squared is 2 times an integer, which is going to be an even integer. So this 2q squared is an even integer. It's an even integer. Which means what? P squared is an even integer. P squared is an even integer. P squared is an even integer, as you can readily see, because it's 2 times an integer, therefore an even integer. Now, if p squared is even, can p be odd? No, because the square of an odd number will always be an odd number. 1 squared is 1, 3 squared is 9, 5 squared is 25, and so on and so forth. So, if you square an odd number, you'll always get an odd number. Therefore, if the square of a number is an even number, if the square of an integer is even, then that integer must also be even. Which really means that p should also be even. Why? Because if p is odd, square of p could not have been even. So if p squared is even, p has to be an even integer. Now, once we come to this conclusion, every even integer can be written as 2 times an integer k. 2 times an integer k. See? Isn't it? That's the representation of all even integers. It's 2 times any integer. 2 into an integer would be an even integer. Isn't it? So then, if p is even, do you realize that p could be written as 2 times another integer, right? So I could write p as 2 times an integer k. I could write p as 2 times an integer k. Now, having said this, can I remove the clutter from here? Just create room for you. Can I remove this portion off? So p is an even integer then. If p is an even integer, p could be written as 2 times k. P could be written as 2 times k, where k is an integer. If p is an even integer, p could be written as 2 times k, where k is another integer. So plug in the value of p. This is 1, this is 2. Plug in the value of p, which is 2k, in equation 1. So when you plug in p equal to 2k in this, you get 4k squared. Isn't it? P squared means 4k squared is 2q squared. Which means I get q squared is 2k squared. Q squared is 2k squared. Yes or no? Right? Now, another implication of this fact, q squared is 2k squared. K is an integer, right? So k squared is an integer. 2 times an integer will always be an integer, which means this is an even integer. 2 times an integer will always be an even integer. 2 times an integer will always be an even integer. What does that mean? If q squared is an even integer, can q be an odd integer? No. Because square of an odd will always be odd. So Q cannot be odd. Q has to be even. Now, which really brings us to the following conclusion. Q is even. Q is even. That means Q is divisible by 2. Q is divisible by 2. And what we got earlier was that P is also even. We got P as even and we got Q as even. But what did we start with? We started with expressing root 2 as ratio of two integers in their lowest form. Ratio of two integers in their lowest form. So if P by Q was the lowest form of expression of root 2, then P and Q couldn't have had any factor other than 1 in common, right? But what did we end up getting? We end up getting P an even integer, Q an even integer. And therefore, it contradicts this premise. It contradicts the premise that P and Q have only 1 as the common factor. In fact, P and Q now have 2 as a common factor. Why? Because P and Q both are even. If P and Q are both even, then they have 2 as a common factor, not just 1. And therefore, P and Q are no longer co-prime. P and Q are no longer relatively prime. That means root 2 cannot be expressed. It leads to a contradiction. It leads to a contradiction. We started by assuming that P and Q have only 1 as the common factor on the pretext that root 2 is rational. When we assume that root 2 is rational, we started by saying that root 2 could be expressed as a ratio of two integers P and Q, where Q is not 0, and P and Q, P by Q is in the lowest form of expression. That means they have only 1 as the common factor, but it turned out by suitable manipulation that P and Q have 2 as the common factor. That means P and Q are no longer relatively prime, and therefore if they are no longer relatively prime, it leads to a contradiction. It contradicts one of the assumptions that P and Q have 1 as the only common factor. Therefore, what must be the problem? The problem must be the basic assumption that root 2 is rational. Why? Because when I assume that root 2 is rational, I got a bizarre result. It contradicts this premise of assumption. I got a result that contradicts this premise of assumption, and therefore the whole basic assumption about root 2 being rational leads to a contradiction, must therefore be incorrect, inept, and unacceptable. Therefore, root 2 is rational, is incorrect. We've been able to establish this with the help of what's called the method of contradiction. Assume the contrary of what's required and end up getting something that's irresponsible and bizarre, incorrect and inept. And once that happens, the basic assumption turns sour, turns incorrect. Conclusion, therefore, that there is a flaw in the basic assumption. The flaw in the basic assumption is root 2 is rational, is incorrect. Root 2 therefore must be an irrational number. So root 2 turns out to be an irrational number. Root 2 therefore is irrational. Now, so this invariably, to establish that a number is irrational, we will have to deploy what's called the method of contradiction. It's called the method of contradiction. Root 2 is irrational, is established not by direct means, but by means of what's called the method of contradiction. Now, in exactly the same way, I'll come to that later on, but let me tell you that exactly the same way we'll be able to express that root 3 is also irrational. Now, some basic properties which I want you to take notice of. I want you to ponder over these properties. A rational number, when you multiply by an irrational number, you will always get an irrational number. A rational number, when you multiply with an irrational number, you'll always get an irrational number. For example, root 2 is irrational. Root 2 is irrational. And if I multiply it with a rational number 1 by 3, 1 by 3 is rational, root 2 is irrational, this will always be irrational. This will always be irrational. That's a very important property. A rational into irrational will always be irrational. Right? Why? Because, again, using the method of contradiction, say rational number 1 into irrational number 2, let's say, is rational. Let me assume the contrary. A rational number, one number, an irrational number, the second number, let's say is a rational number, the third number. Let's assume the contrary. The statement that I made is rational into irrational will be irrational, but I am assuming that a rational into irrational is a third number, which is a rational number. I am contradicting the statement. Now, what does it lead to? It leads to irrational 2 equals irrational number. This number is rational number. Call it this, divided by rational number, call it this. Now, what's the element that's bizarre here? In our previous section, we learned that the ratio of two rational numbers will always be rational, isn't it? We learned that the ratio of a rational divided by a rational is always rational. But what have we obtained from this? A rational divided by another rational, we end up getting an irrational. So this is a contradiction. Where does this contradiction come from? What's the origin of this contradiction? The origin of this contradiction is an incorrect assumption. The assumption that rational into irrational is rational, therefore is incorrect. And therefore a rational into irrational cannot be rational, must therefore be irrational. Always a rational number multiplied by an irrational number will always be an irrational number. Now, let's look at some more properties. In exactly the same way, a rational, this I want you to establish yourself, divided by irrational, a rational number divided by an irrational number, or an irrational number divided by a rational number. Ratio of a rational to an irrational or an irrational to a rational will always be irrational. This will always be irrational. Ponder over this. Please ponder over this. Ratio of rational to irrational or irrational to rational will always be irrational. Let me look at some more aspects. A rational plus irrational. Let me call it rational 1. Let me call it irrational. This is the second number. A rational number plus an irrational number will always be an irrational number. Got it? Number 3. Whenever you add a rational to an irrational or you subtract a rational with an irrational, you always get an irrational number. For example, if root 2 is irrational and if you add to root 2 minus 1 by 3, which is a rational number, this is a rational plus irrational. This will always be irrational. Now, how does one establish that? Same thing. The method of contradiction. To establish that something is irrational is invariably attained by using what's called the method of contradiction. Now, what we assume is Let me assume the contrary. Let me assume that rational plus irrational is rational. Rational 1 plus irrational, let me assume, is rational. Let me assume is rational. Let me assume is rational. Let me assume that a rational plus an irrational, call it 2, is rational. What I want to establish is that rational plus irrational is irrational, but I'm assuming the contrary. I'm assuming that a rational plus an irrational is actually rational. Now, what would this lead to? What would this lead to? This is an assumption which is contrary to what we want to prove. I'm assuming that a rational plus an irrational is rational. But what we want to establish is that a rational plus an irrational will be an irrational. So I'm deploying what's called the method of contradiction, assuming the contrary of what's required. Now check that out. If this is true, then this rational minus this rational turns out to be irrational. Yes or no? Then this rational minus this rational turns out to be irrational. But didn't we learn in our previous section that difference of two irrational numbers has to be a difference of two rational numbers has to be a rational number? Didn't we learn that in our previous section? But what we end up getting is rational minus rational as irrational. That's not true, because difference of two rational numbers will always be a rational number. We get the contrary of this, rational minus rational, we end up getting is irrational. So which leads to a contradiction. Where is the flaw? The flaw is in the basic assumption. The assumption that rational plus irrational is rational must therefore be incorrect. Rational plus irrational must always be irrational. Must always be irrational. This is another very important property. Rational plus minus irrational will always be irrational. Now, rational to the power rational. This, like I mentioned in the previous class, in the previous section, can be rational as well as irrational. For example, 2 to the power half. It's rational to the power irrational. It's rational to the power rational. Rational to the power rational, which is irrational. I could also have 2 to the power 2, which is rational to the power rational, which is rational. So rational to the power rational could be rational as well as irrational. Now what about the following? Irrational to the power rational. Irrational to the power rational. What about this? Will this be rational or irrational? Can't say. Because, say, I take an irrational number root 2. Let's say I take an irrational number root 2 and I raise it to the power 2. 2 is a rational number. So this is irrational to the power rational, and this turns out to be rational. This turns out to be rational. Right? This turns out to be rational. However, if I took root 2 to the power half, root 2 to the power half, root 2 is irrational, half is rational. So this is of the same form, irrational to the power rational, irrational to the power irrational. This is actually 2 to the power 1 by 4, which we can establish is irrational. So irrational to the power rational can be rational as well as irrational. And rational to the power rational can also be rational as well as irrational. So these are some of the basic properties of irrational numbers, right? Take notice of this. Sum of two irrational numbers, sum of two irrational numbers. What about that? That means irrational plus irrational. irrational plus irrational. That could be rational as well as irrational. For example, I take one irrational number as root 2. And I take another irrational number as minus root 2. Root 2, if that's an irrational number, then minus 1 into root 2 will always be irrational. So this is irrational. This is also irrational. Why? Because if I multiply an irrational number with minus 1, that will also be an irrational number. Root 2 and minus root 2. Both are irrational. But when you add them up, you get 0, which is rational. Right? So sum of two irrational numbers can actually be rational. So this can be rational as well as irrational. We cannot say. In fact, we'll be able to prove that root 2 plus root 3, which is sum of two irrational numbers, will be irrational. We'll be able to prove that shortly. So sum of two irrational numbers can be irrational, or sum of two irrational numbers can be rational. So we cannot very conclusively say whether sum of two irrational numbers is rational or irrational. That's case dependent. This much for this session. More on rational and irrational in the session to follow. Thank you so much.